At this point, let's do an example of Rankine vapor power cycle with regenerative open feed water heating. And I believe this is problem 838 from the textbook. Okay, let's label what's going on here. So the problem says, state 1, the inlet to the turbine is at a pressure of 100 bar and a temperature of 480 degrees Celsius. And the intermediate pressure is 7 bar, coming for the fraction of the fluid that's bled off after the first turbine. The turbines have isentropic efficiencies of 80%. The condenser operates at so P3 equals P4 equals 0.06 bar. The pumps also have isentropic efficiencies of 80%. And the open feed water heater exits as a saturated liquid. Okay, I think I've got everything. Let's move over here to our TS diagram and see sort of what that looks like. My temperature, again at state 1, is 480 Celsius. I've got 3 different pressures in my problem. I've got 0.06 bar at the condenser. I've got an intermediate pressure of 7 bar at the exit of the first turbine. And then I've got a pressure in my steam generator of 100 bar. Okay, and then I've got the isentropic efficiencies shown for my first turbine, for my second turbine. Let's see, the pumps also have isentropic efficiencies. So this is actually state 5S, the isentropic performance. And then this would be real state 5. And then for the second pump, this would be state 7S, the isentropic state. And that would be the real state 7. Okay, let's try to analyze this cycle. We'll work our way around just like we've been doing, trying to find each state to identify the enthalpy as our primary goal, because we know that will drive the work and the heat transfer. Let's start with state 1. State 1, we know pressure. We know temperature. We could go to our tables or use software to understand, hopefully by now we're in the superheated region, and we can find enthalpy. And we can find also entropy. State, let's see, next up is state 2S, which would be the isentropic exit of the first turbine. For state 2S, let's see here, we know the pressure, 7 bar, and we know the entropy, 2 properties to fix the state. And in this case, the drawing is accurate. It falls in the 2-phase region. Again, the steam table procedures algorithm or sheet could help you deduce that and find the properties. So for state 2S rather, I end up with 2,684.8 kilojoules per kilogram. state 2 representing the real state exit of the turbine. I can use the isentropic efficiency definition. So that would look like the real work produced by the first stage turbine divided by the ideal work produced if there were no irreversibilities. So using that, I can plug and chug at this point and obtain the enthalpy at state 2. Let's see here. I'm also going to need, at this point, I know the pressure and I know the real enthalpy. I can go to the tables and determine the entropy at state 2. Okay, so from state 2, I'm now looking at my second stage turbine, and I'll identify the ideal state at the exit, state 3S. What two things do I know at state 3S? I know the pressure, and I know the specific entropy. Two properties, I can fix the state, and I can find that my quality is less than 1. I'm in the 2-phase region. I can also find my enthalpy. Okay. Now I can find the real exit of my second turbine, state 3, using the isentropic efficiency definition. And plugging and chugging. I obtain the enthalpy. Okay, that gets me to state 3. 3 to 4 is my condenser. State 4, I know I'm a saturated liquid. So therefore I know the pressure at state 4. It's given to me. And I know the quality at state 4 is 0, saturated liquid. So the saturated tables, I can locate the enthalpy. Next up is state 5S. Which is the ideal exit of the pump. And for that, I use the definition of the isentropic efficiency of the pump. And oops, this is ideal, so I'm not applying the isentropic efficiency yet. This is where actually I remember that my definition of the specific work of the pump is equal to the enthalpy at state 5S minus the enthalpy at state 4. The issue with the pump is that it's not a temperature change device, it's a pressure change device. We can go back to the previous, a few lectures back on reversible work of a control volume and see that I can model this more closely, assuming incompressible fluid by the constant specific volume and the pressure change. Okay, so therefore I can calculate state 5s using the enthalpy at state 4 plus knowledge of the assumed constant specific volume and the pressure change. There's going to be some unit conversions there that you should be able to reproduce that I've got 152.23 kilojoules per kilogram representing the enthalpy at state 5s. Get this out of the way here so I can continue working. Next is the real state 5. And for that, I have to utilize my definition of the isentropic pump efficiency. Again, that's defined as the ideal amount of work it takes to drive the pump divided by what it would take in reality, which is a larger number to overcome all of the irreversibilities such as heat transfer, friction, etc., etc. So I can solve for my unknown, the enthalpy at my real state 5. And plugging and chugging, I get 152.41 kilojoules per kilogram. Let's see here. State 6. I know two things to fix the state. I'm given the pressure, which is 7 bar, and again, I know the quality. I assume for pumps that I start at saturated liquid. So the steam tables allow me to calculate my enthalpy, or determine my enthalpy rather. Now I go from state 6 to state 7. Again, this is the ideal exit of the pump. I model that as the reversible work of a control volume, similar to what I did at state 5s. And I'm able to stall for state 7 using knowledge of the enthalpy at state 6, and then also the reversible work of a control volume representing the pump, the ideal pump. Oops, this is state 7s, the ideal exit. Okay, and plugging and chugging, keeping track of units. I end up with 707 kilojoules per kilogram. And then finally state 7 represents the real exit of the pump. And again, I use my definition of the isentropic efficiency of a pump, which would be the ideal work that it takes to drive the pump, divided by what it takes in reality to drive the pump and overcome the irreversibilities. I can solve for my unknown. And plugging and chugging. I get 710 kilojoules per kilogram. Okay, let me block off some space here to continue. I've gone through the state, or the cycle, in gory detail, and I've determined the properties at each state in the cycle. Okay, now I can start calculating performance numbers using the first law for each of the components, as I did previously. Let's do that. So the heat transfer in is equal to this is specific heat transfer, enthalpy at state 1 minus enthalpy at state 7. I end up with 2,611.3 kilojoules per kilogram. And again, that's based on the rate of heat transfer divided by the total mass flow rate of my cycle. While we're talking about that, what is the fraction of flow that's diverted out after the first turbine? Again, this equation came from applying my first law on the open feed water heater. I can plug and chug and end up seeing it's about 20% is the bleed off after my first turbine. I can determine, let's see here, the work of my specific work of my 2 turbines. Plug and chug, I get 962.96 kilojoules per kilogram. Let's see here, for the pumps, I can plug and chug. And again, these equations are coming from the previous material, applying the first law of thermodynamics to each of the control volumes and writing it as the heat transfer work divided by the specific to the total mass flow rate of the entire cycle. And finally here I can calculate the thermal efficiency of this specific Rankine cycle. That's going to look like the specific work of the turbines minus what it took to drive the pump divided by the heat transfer into the cycle. That ends up looking like just short of 950 kilojoules per kilogram divided by 2611. And I end up with 0.364 or 36.4% thermal efficiency for this cycle. And this uses, I believe, fairly similar data compared to some of the previous problems, so you can go back and compare and see what kind of performance improvement you get in terms of thermal efficiency. Yes, the work is less, but realize the efficiency is higher. Therefore, the heat transfer in is also less. So if you were to normalize this to the same level of heat transfer, you'd see you get greater work output using a Rankine cycle with open feed water heater compared to just using reheat or just relying on superheat.